It's
Yeah.
sad.
Easy. Yeah.
Right. So we continue our discussion of exercise number 14. So just quick question. Can you hear me and can you see my screen?
Yes, we can hear you.
Okay.
We can hear you.
Can you see my screen? Yes. Can you see my screen? Share my screen.
Yes, yes, sir.
All right. So we actually started our conversion process, right? Just basic arithmetic we're doing today, tomorrow, probably Monday as well, and throughout next week. Actually, turns out that what we're doing is just basic arithmetic, and in fact, as it pertains to how exactly the computer gets to perform those arithmetic operations. This is a focus of this course, actually, right? So from the time we start discussing binary representation all the way up to signed magnitude, how signed and unsigned integers are represented in the computer, one's complement and two's complement. This is all centered around how a computer gets to perform operations. We have been singing all along about how a computer does nothing more than perform very basic arithmetic operations. And specifically, I would like to draw your attention to the key function of this thing we introduced as the ALU, the arithmetic logic unit, right? So what we're going to be doing going forward, especially beyond our discussion of binary representation here, is trying to understand exactly how that's done. It turns out really that everything boils down to addition and subtraction. Multiplication can be viewed as addition and subtraction. Surprise, surprise. This is what we're doing in this course, right? So I don't know if there are any questions with regards to the basic conversion from hex to decimal, which we did. Very easy stuff. Hopefully everybody has gotten to a stage where if you're given, right, something like this, say, Lighton's IPv6 representation of his address is this notation here. Can you convert it to the decimal notation? It's represented in hexadecimal, right? Can you represent this into its equivalent decimal notation? It should be fairly easy, right? Because we discussed this. Same process, right? Those steps that we discussed where you start by, so for each one of, in this case, you'd have a decimal equivalent of this, of that, of that, of this, and of this. And I know what you're thinking, don't do that, right? You're thinking, I will use the calculator. Okay, fine. You can use the calculator, but you need to show working also, right? But what we're saying is that for each one of these numbers, you should be able to do what we did yesterday. Was that yesterday? I guess. What we did yesterday, when you pull out this number here, and you go through those series of steps that we introduced. So for a hex number like this, right? And you remember this, is this supposed to be uppercase or lowercase? Well, I said it's agnostic of that, right? So you go through the steps that we talked about by first of all coming up with the decimal notation for all of these hex symbols, not digits or numbers, symbols, right? Yes, 15, 14, is it? 8, 0, is it? Yes? What else do? You come up with, from right to left, you come up with powers of 16, right? So power 0, power 1, power 2, and power 3. You compute the powers, the powers of 16, you evaluate them. So 16 to power 0 is nothing more than 1. They told us this in grade 1, that anything to the power 0 is 1, right? I think it's necessary school now. And then this is just going to be 16, right? This is just going to be 6 or something, right? This is just going to be, I don't know, 4096. After you do this, the next step is for you to multiply the derived decimal symbols or digits, if you want to call them digits. You multiply them with the evaluated powers of 16. So in this case, we are going to multiply 15 times 4096. And here we're going to multiply 256 times 14. Then here we are going to multiply 16 or 8 times 16 or 16 times 8. It's all the same, right? 8 times 16. Here we are going to multiply 0 times 1. What is 0 times 1? They said it's 0 apparently, right? And then the last step is we add, right? So we add this, and this. Sorry, this, and this, I guess. Then we come up with 65,152, right? So hopefully we've done the right thing, I guess, I don't know. So we can use our calculator to verify. By the way, you're allowed to use calculators in the exam. So if ever is a question on conversion number systems, probably the easiest question, because you can work behind, right? You can compute the answer and then you work behind. So what we were saying is that FE80 should be equal to 65,152 base 10, right? That's the thing, right? So you find in literature, right, very weird things like numbers that are represented like this, right? FE80. That's a convention rather. In certain instances, can I finish first? In certain instances, a hex number is represented by a 0x prefix. In certain instances, a hex number will be explicitly stated as a hex by using a superscript, right? So you would have something similar to what we have here. I can't write a superscript in text editor here, so I have to do it here. So you have something like hex or hex uppercase, and then you'd, oh wow, is it comma or something? No, don't know, I'll use this. Forgotten the shortcut. So, oh, Control-Shift-B, wow, okay. Control-Shift-B, right? So in certain instances, this is how it's represented. In some instances, FE, oh, sorry, Control-F-B. FE still superscript here. I have to change this. In some instances, it will be represented like so, base 16. It's one and the same thing. I just wanted to put it out there, but sometimes numbers, a hex number will be represented like so, sometimes like so, other times like so. Other times like so. One and the same thing. And this is especially important when you're working with symbols that recycle the same symbols as what appears in base 10 numbers, right? So if I just had a number like this could be a hex, it could be a decimal, right? Which is why when you're dealing with number systems, you have to be explicit. If you see something similar to this, and you know that it's a hex number. Yes, was the question?
Yes, sir. So if you're told to convert the values with variables like FE80 and the others, you only convert the ones with what's the term? Okay, you only convert the ones with the variables, but the ones with the numbers, you just leave them like that.
By converting, what do you mean leaving them like that?
Can you go back to the previous screen? Yes. You only convert the ones with letters and leave the ones with numbers only.
No, the conversion process, it needs to take into account everything.
Oh.
Unless if you're talking about the first step where you're deriving the equivalent decimal symbols. I mean, because deriving the equivalent of 8 hex is 8 base 10, right? 8 base 16 is equal to 8 base 10. You understand what I mean? 0 base 16 is equal to 0 base 10. So you could either do that as part of step 1, or if you want, I mean, you could leave it out. Nobody cares, right? So if you're talking about this step here, then yes, right? This step, it doesn't matter whether you say what is the equivalent base 10 symbol for 8 base 16. This is going to be 8, right? But otherwise, everything needs to be taken into account here. If you look at this process here, everything, right? So for this question, you do this process here, you convert this going through this process, you convert this going through this process. Now, if I were you, what I would do is I would come up with a very nice Excel formula for converting hex into decimal numbers, hexadecimal numbers into decimal numbers to practice your skills introduced in EDU 1020. You see those formulas you're being taught in EDU 1020 when dealing with spreadsheets? You can do what Lighton is doing right now, right? Practice, practice, practice. Great stuff. So,
So
yes, sir.
what I meant was that slide, the previous one,
Next slide.
the one with the full IP address. Do you only convert the hexadecimals with letters, or also the ones, because the ones with numbers, they're just numbers only? No,
Yeah,
before
but the
this,
thing is,
before this
the
one.
thing is, someone tells you to say this thing, like you're saying FE80 full colon 20C, full colon 29FF, full colon FEFF, full colon 6697. If you are told that this is a hexadecimal number and you have to convert it to, if you're given this and you're told to convert it to decimal, it's in hexadecimal. So for you to convert it to decimal, you have to convert everything that is a part of this representation, irrespective of whether you have a number like 4689. It's still hexadecimal. You see this? I know this. Your question is associated with this, right?
Yes, sir.
4689. The thing, if you're told 4689 is in hexadecimal, the equivalent representation for decimal is going to be completely different. And let's not go through the boring stuff of re-evaluating this, right? 4689 in decimal is 18,057. For you to arrive at 18,057, you must go through, might as well do this right now, right? You must go through the same process, right? Hexadecimal number, this. How do you convert this? Step one, all these symbols, 4689, must be, you get the get equivalent decimals, right? Decimal symbols or something. Now, equivalent decimal symbol is still going to be this. So what you do, you still work with, you're still working with the same. It's 4, 6, 8, 9. So no point in doing this. What's the next step? Powers of 16. From right to left, beginning 0. So 16 power 0, 16 power 1, 16 power 2, 16 power 3. What's next? Evaluate powers of 16. You notice that we're going through the same step. What is 16 to power 0? I'm using my spreadsheet, it's 1, right? 16 to power 1, 16. 16 to power 2, 56. 16 to power 3, 4096. What's the next step? Product of decimal symbols and evaluated powers of 16, right? How do you do this? You just multiply. In this case, it will be the equivalent decimal symbols 4 times 4096. In here, it's going to be 6 times, it's going to be 6 times 256. In here, it's going to be 8 times 16. You must ask these questions if they don't make sense, right? This must make sense. In here, it's going to be 9 times 1. What's the final step? Add products or get sum of products. Or just adding here. We can use the sum that was introduced in EDU 1020, right? And then we find this as 18,057, right? So it's really not that hard, I guess. Is this making sense now? I don't know if I answered your question.
Yes, sir. Yes, you've just answered my question, sir.
Yeah, okay. All right, so the question now, right, is I mean, so now that if we can convert from hexadecimal to decimal, the question is how exactly do we do the opposite, right? And this question came up yesterday as well. It turns out it's not that hard. You're doing the reverse, right? You're multiplying and whatnot. You do the reverse by performing what's called repeated division, right? And so the way you do this is you repeatedly divide the decimal number that you have. If you're converting from decimal base 10 to hexadecimal or base 16, you repeatedly divide the decimal number by 16, which is the base you're converting to. And the specific process you follow here is you construct the equivalent hexadecimal number by taking into account the remainders as you are repeatedly dividing the decimal number by 16. Don't worry, this makes sense very soon, right? A key thing to take into account here is as you are repeatedly dividing and taking note of the remainders, if you have a remainder that is greater than or equal to 10, you must remember, if you have a remainder that is greater, it rhymes, right? That is greater or equal to 10, you must remember to convert those numbers that are 10 and above to represent them using these symbols, the hex symbols, A through F. Because hexadecimals do not have, there's no 10 in hexadecimal. There's no symbol. In hexadecimal, we don't have a symbol 10. No, or 11, or 12, right? These are represented by these alphabetical letters, A, B, C, all the way up to F, right? Remember this. So again, we'll go through some examples here for you to understand. So here's what we do. Repeatedly divide, and we're going to look at these two examples to see exactly how we do this. Very simple stuff. I'm saying in class 11, 10, I don't know. Okay, I don't know what I was saying here. So we'll go through these two examples to see how we do this, right? So remember, you're repeatedly dividing by 16. You first of all set the quotient to be equal to the decimal number that you want to convert to hexadecimal. In this case, we are trying to convert 1110 or 1110 base 10 into base 16. So we will repeatedly divide 1110 by 16. The quotient is going to be 1110. The divisor is going to be 16. What we will be doing, I would like for you to, well, for those of you that don't already know how to do this, I don't know why we're doing this anyway. I know people already know this. I would like you to pay particular attention to what's going to happen to the remainder here, right? The result and the remainder. Result, remainder, right? This is where the stuff happens here. So repeated dividing by 16, we're saying we will divide 1110 by 16. It turns out that 1110 divided by 16 is 69. Is it 60? Yes, it's 69, remainder 6, right? And we can confirm this using my nice calculator here. I think it would be nice if we use the calculator. 1110 divided by 16 gives us 69, right? Remainder is 6. We know how to get the remainder, right? It's the same stuff we were taught in grade 1. I think it's I don't know if they call it reform school before you get to grade 1 or something. I don't know what they call it. But for you to get the remainder, what you do is you multiply you know this, I know why I'm doing it, 69 times 16. And then you subtract it from 110, right? Now the remainder is 6, right?
So,
Yes, sir.
you can also get the same answer by multiplying 0. The decimal numbers, 0 and the decimal numbers by 16.
Yes.
You get the same answer.
There we go. There's smart people here, right? Now, the successive generations are always smarter. Yes, indeed, it is true. Here's the other thing here, and I hope this sinks in. The fact that what I'm showing you here, the methods that I'm using here, it's not like these are the only methods that are out there for you to be able to derive equivalent answers of different number systems, right? Or different bases. I'm just using one of many methods, and hopefully there are many methods out there, right? So do not be deceived that just because Lighton was using this method, then Lighton is going to expect you to use this method. No, right? This is just a means to an end. I'm just showcasing, I guess, probably the easiest of methods here, right? And I've seen this before, right? Where you have somebody, they think that they are also supposed to do this in the exam. You draw a box. No, ladies and gentlemen, it's not like I expect you to do this. You can derive your answer in whatever way you want to derive, right? As long as you show the steps, the derivation steps or process you went through. I hope that sinks in. So yes, thank you very much. identifying the remainder is 10 divided by 16 is 69. You just subtract 69. You get this answer, you multiply by 16 to get 6. Right? So essentially, when you repeatedly divide the hexadecimal number by 16, you just get everything after the decimal point. So you have 0.375, and then you multiply this by 16, you get the remainder. What you're interested in is the result, the answer, which you're going to use as a quotient, and the remainder. Good stuff. All right. So we're saying the next step here is we are going to repeatedly divide what we had as the answer, which was 69 by 16. So we're saying 69 divided by 16 is going to give us 4.3125, or rather just 4. What is the remainder? We're just going to, use Snyangwe's method here, we'll subtract 4, then times 16. It's much better, I guess, not as confusing. Remainder is 5. We repeatedly divide 4 by 16. 4 divided by 16, they said it can't or something, but we know here it's 0, remainder 4, right? So 4 divided by 16, the answer is 0, remainder 4. The point when you get to a 0 here, when you get the answer of 0 is when you stop, right? And your answer is going to be what you have on the far right here, the remainders from bottom to top, right? So the answer is going to be 4, 5, 6, base 16. Right? Is this making sense?
Yes, it is.
Yes, sir.
Okay. Yeah, I know it's simple enough. So I mean, the same process here. I think we're already good. We're good at this. So we don't really have to waste a lot of time here. So with 79, it's the same process. What we're saying is that we repeatedly divide 79 by 16. So 79 divided by 16 is going to give us 4. The remainder is 15. Now, this is where it gets really interesting. If you look at this particular case, the remainders were hex symbols 0 through 9. But in this particular example, the remainder here is 15, right? So 1679 is 4, remainder is 15. 16 into 4 is 0, remainder is 4. Now, some people will get confused here, right? Say, well, but I found 4 and 15, and you make the mistake of thinking the answer is 415. No, it's not 415. Why? Because for any symbol any answer we get that has a remainder that is greater or equal to 10, we must remember to convert that number to its equivalent hex symbols, A through F, right? So in this case, 15 is going to have to be F here. So the answer is going to be 4F. Do you understand here?
Yes, sir.
Here's a question for you. What is 9 base 10 in hexadecimal? How do we do this? How would we evaluate 9 base 10 into hexadecimal? What is the answer?
Isn't it 9?
29.
9.
It's 9.
Yeah.
It's
there we
9,
go.
sir.
Thank you very much. What is 16 base 10 in hexadecimal? How would we do this?
That's F.
Really?
256.
That's interesting. 16 base 10 is F, right? Okay. Thank you for that, right? So it turns out that sometimes it can get a bit confusing here, but you must remember to repeatedly divide. Whatever number you have, remember to repeatedly divide. How do we do this? We're saying first step is we repeatedly divide 16 by 16, right? What is 16 to 16? The answer is 1. Remainder
0.
0, right? Remainder 0. Right? What is 16 into 1? The answer is 0. Remainder 1. When do you stop? You stop when you have your answer equal to 0 as you are dividing. And so the answer that you have is 1, 0, base 16, right? So the answer is actually 10 base 16. The first time, follow the steps, right? Whatever steps you're using, follow them religiously until it sinks in, until it becomes muscle memory or something. And surprise, surprise, these things are going to become muscle memory very, very soon, because when you revise these number systems, you revisit these number systems next year. I think there's a course called computational maths or something, I don't know. These are coming back again when you start looking at data and communications networks, because it turns out that when you're subnetting networks, I mean, there are number systems that you play around with. So this should become muscle memory very, very soon. And it's not that hard really to remember these things if you just follow through with the steps. Right? All right, so 4F, right? Here's I'm going to leave you with some few examples here. We won't go through these unless if you want us to go through these here. But please find time and go through slide number 58. Try and see if you can convert that serial number. I'm getting this from my Android device, by the way. On my Android device, this is a serial number for one of my Android devices, right? BD565AE0. Assuming this is a hexadecimal representation, what is the equivalent? Base 10 number, right? So see if you can work through this. Now, you notice that the larger the hexadecimal number you're working with, by the way, its conversion is hex to decimal. The larger the number, the larger the decimal number you're going to be working with. Why? Because of the powers of 16 you're working with. 0, 16 power 0, 16 power 1, 16 power 2, 16 power 3, 16 power 4, 16 power 5, 16 power 6. Right? So the magnitude is going to be much larger. Right? See if you can do that. See if you can also convert Lighton's IP address when he was creating these slides. I'm not sure if I was connected to microlink or if I was connected to something else here. See if you can do this, right? Here's the other thing, right? Can we convert, assuming this is base 10, can we convert this to base 16? This is not in base 10. Can we convert this to base 16 or something? Can we convert this Wi-Fi MAC address, which is a unique identifier for the hardware device that you're using, into its equivalent decimal notation? It's not that hard, right? In my opinion. Can also convert that Bluetooth address, which is in base 16. Can we convert it to base 10? Right? Do you suppose you can do this? I want to ask if you can do this. Unless if there are any questions, I want us to quickly transition to so-called base 2 or something, or binary representation. Any thoughts about what we just looked at? Any confusing parts?
Oh, sorry, Dr. Lighton. Tomorrow I missed class. I'm scheduled to rewatch the video today. And I'm just asking about the 4 colons. You said that on part of the 4 colons, what do you replace when you are converting?
No, so usually, right, a conversion, like a more a practical conversion like this. And if you look at the past exam questions, we've had practical conversion problems like this, right? So if you're given a practical problem like this to say, can you convert this IPv6 address into its equivalent decimal notation? You're given a number like this. The expectation is that when you're converting to decimal, you are going to represent it in the same format. So you preserve these 4 columns. So all you're interested in is you're converting these numbers here. This is nothing more than, usually the question will specify, right, to say the 4 columns are just there to segment the different portions of the number itself. The same goes for a normal IPv4 address. If you're given a question, and we probably had this in the exam last year or something, or maybe previous year. You're given a question like this to say this is the IP address in dotted decimal. Can you represent it in dotted hexadecimal? All you're doing is you're just converting these numbers here, right? And you're preserving the period. So the period is just the syntax of trying to properly represent the IP address. right? They have no other significance other than just aesthetics. They're just there for aesthetics. So what you do is you convert 192 to hexadecimal. So this would be like C0 dot, you convert 168, which is A8 dot 43. Now I'm cheating now, right? 43, so about that. 43 in hexadecimal is 2B dot 40 in hexadecimal is going to be 28, right? So this would be your answer. And obviously, the other way of representing this answer is by using lowercase letters. Nobody cares, right? It's one and the same thing, to 28. It would be weird if you were to represent it using camel casing, right? Where, who does this? Sorry? It'd be cool, I don't know.
Oh, thank you. I've understood.
Yeah. Is this making sense? Are there any other questions with regards to conversion the other way? No
Sir,
question. Yep.
kindly go through the same example, please. I missed out on some part.
Which same example?
The one you just did, converting from back to hexadecimal from base 10.
This.
Yes, that.
Oh, I mean, it's so what I was saying is, depending on the question, if you're given a question like this, right? What you're doing is you're going to have to, whatever answer you get is going to have to preserve the formatting here. So what we're saying is, if you're given a question, say, can you convert this IP address to its equivalent dotted hexadecimal representation? What you'd have to do is you're going to convert 192 to hexadecimal, 168 to hexadecimal, 43 to hexadecimal, 40 to hexadecimal. So if in effect, what you're doing is, I guess we might as well do it. You do it stepwise. You're first of all going to convert 92 base 10. You convert 92 base 10, right? Ooh. You're going to have to convert 92 base 10. And then you have to convert 168 base 10. Ooh. I hate spreadsheet applications sometimes. And then you'll have to convert 43 base 10. Right? And then finally you have to convert 40 base 10. So you notice it's for such a question. I mean, so converting 192 to base 10 is not a problem. All you do is you take advantage of repeated division, right? Repeated division. 192, you repeatedly divide this by 16. What is 192 divided by 16? The answer is 12. Remainder, and I'm going to have to do this, just leave it 10 decimal. Wow. Is this true? No, it can't be true, right? There's no 192 into 16 goes into 182 without any remainder. Okay.
Yes, sir.
Okay, great. So thank you. So we repeatedly divide 92, right? Remainder. So 182 into 16 into 192 is 0. I'm sorry, it's what? It goes into
12 remainder.
12 remainder 0,
0.
right? 16 into 12 is 0, or it can't, right? As they said in grade school or something. Remainder 12. Now this is where it gets really interesting, because we said that for anything that's above 12, above 10, we have to use the symbols. We know A is 10, B is 11, C is 12. So this is going to be 0, this is going to be C. Right? And I guess I'll have to, we do what Mr. Mwalimu is teaching us so that the aesthetics are good, right? So, and then you do it, you flip it around, bottom to top. So in this case, the answer is going to be C0. Do you understand? Or I guess C0, right? You do the same thing for 168. You repeatedly divide 168 by 16, and then you keep track of the remainder, right? Do apologize here. I should maybe reduce my, I hope this is still legible enough, right? So you do the same thing for 168. You say, what is 168 divided by 16? The answer is 10.5. So we're just going to round this. Let's say 5 decimal points here. Right, so 10.5, and if we use the method that Sinyangwe taught us, would say the answer here is, now let's do this the right way, I guess, at least we confuse people, right? At least I confuse myself. 168 divided by 16 is 10. Remainder, what is the remainder? I don't know, right? 0.5, right? 0.5 times 16 is what we're interested in. So 16 to 168 is 10. What is the remainder? The remainder is going to be 0.5 times 16, right? Which is 8. Yeah? 16 into 10 is going to be, if you can't, right? It's like 0, remainder 10. But remember that we need to convert anything that's 10 and above to the equivalent hex symbols. 8 is going to be preserved, 10 is A, right? So meaning that, I guess I have to do what Mr. Mwalim is teaching us in spreadsheet applications here. So the answer here is going to be A8. Bottom up, right? A8. So we do the same thing for 43. We repeatedly divide 43 by 16. Then we say what is we have a remainder here. We say what is 43 divided by 16? 2, right? Remainder 11. Okay. What is 16 into 2? No, they said it can't or something, right? So it's 0, remainder 2. We convert everything that is 10 and above to their respective hex symbols. A is 10, B is 11. So this is B, 2 is preserved. Bottom up, 2B. So we come here, it's 2B. We come to 40. I do apologize, I'm shrinking this because I want the thing to be visible enough, the screen, for everything to be visible for you. I guess I could also just do this or something. We do the same thing for 40. We say we repeatedly divide 40 by 16, and we keep track of the remainder. 40 divided by 16 is 2. Remainder, it's remainder 0.5 times 16, which is 8, right? So we have 8 here. 16 into 2, it can't, they say, but it's 0, remainder 2. This is 28, right? You know, we use what Mr. Mwalim is teaching us here. So it's 28. 28. This is making sense. And I mean, you could get funky here and you say 28 by 16, right? Like they always want to do here. Maybe
Yes, sir.
16 to be by 16 or something. Maybe 16. I don't know. It's not that hard. All you have to do is, especially for hexadecimal numbers, you just have to be able to paint that mental picture of the 16 hex symbols. The 16 hex symbols are easy to remember. It's a normal 0 through 9 symbols used in hexadecimal, plus an additional 6 symbols that are derived from the English alphabet beginning A. A, B, C, D, E, F. A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. Great stuff. What is 19 base 16? Can we remember? Can we do this? I don't know. What is 19 base 10 to base 16? More. I thought people have scientific calculators. You can download the scientific calculator from your phone, right? But alas, you won't be able to use your phone here. The answer is 18, right? All right. I don't know if this is making sense. I'm going to have to suggest, I'm looking at the time here. Maybe we can, instead of, I don't want to cut this short, so looking at the time, I'm going to leave this for tomorrow, the binary part, but the 5 minutes remaining, or the few minutes that are remaining, I just wanted to find out if there are any things that you want me to clarify in terms of the conversion from hex to decimal, decimal to hex. I don't know if people had a chance to go through some of the questions from last year, the quiz questions, and perhaps the questions in the test and the exam. If you think there's something that is a bit confusing in terms of the division, if I were you, as you are practicing these, take out a plain piece of paper and actually draw this thing, right? That thing we are showcasing here. You draw this thing where you say, oh, I wish I could showcase the thing I'm talking about here. You draw this thing, right? When you're converting, let's say you're converting 19 base 10, right? You actually come here and you draw on a piece of paper using pen. When you're doing this for the first time, you draw these small little boxes here, or these activities here, or whatever you want to call them, the lines, and then you actually do this, right? When you're doing this for the first time, at least you get confused. Do this stepwise, right? Do this stepwise, and then, so you say 16 into 9, you know that, I mean, this is easy, right? 16 into 9, the answer is, it goes in one time. Remainder 3, right? So you write these things down. It will be like your remainder or something. Sorry, writing using my mouse, I shake a lot, I guess. And then you repeatedly divide 16, 1 divided by 16, the answer is 0, right? Or it can't, 0. Remainder 1. What is the answer? Top to bottom, right? Top to bottom. Always remember, people get confused with this top to bottom thing, right? Remind yourself that it's top to bottom. Some people just think the answer is 31 here because you've forgotten, oh, was it top to bottom or bottom to, or was it top to bottom or bottom to top or something? It's bottom to top, right? 1, 3. Do you understand this? Are there any, do you think you have any questions? Do you think these conversion things are a bit confusing here? So if I was to fire up QtSpim, right? Yeah. If I was to fire up QtSpim and I run a program and I ask you, can you derive the equivalent, decimal equivalence of this status of register number R5, for instance? This integer register R5 or A2, A1, sorry. Would you be able to do this? Hex to decimal. It's easy, right? If the question was to come, say, you have this number here, can you convert this to decimal? Don't know. Are there any questions? Are you even there or something? I don't know. But maybe not.
Yes, Dr.
There.
The question. So,
Yes.
why are we starting from the bottom going up instead of from the top going down?
Well, that's a method of repeating. It's convention. That's how the method works, actually. I don't think there's any. It's a good question, by the way, smart question. But that's the reason. The simple reason is you get the wrong answer if you do the opposite, right? It's part of the process. You know, like it's part of the process, the method of deriving a hexadecimal number from a decimal number. It has to be done that way. Otherwise, you see, if you say it's 31 and you try and work it backwards, right? 31 to hexadecimal gives you something else. It's 1F. Do you understand this? So the reason we're doing this is because the method, this is how the method works. It's of the derivation method. That's how it works. I hope that answers your question. That's an interesting question. Why bottom going up, not up going down, right? It's part of the method. Great question, by the way. Are there any other questions that people might have?
Sir,
Yes.
The other example that you've just given us, 7FF, go back to that question.
Yes, this question, this.
Yes, sir.
So you want us to go through this?
No. I just want to ask. So when converting, am I supposed just to concentrate on the 7, then these F's I ignore them, then I convert the 714?
No. You convert everything. You see, in this case, right? This is hexadecimal. So this question will probably require you to convert this to decimal, right? Converting this to decimal, you have to go through that. Is it a 5-step process where the first step is and maybe let's quickly do this actually. So you don't ignore anything, right? Think about the steps here. So you have this, yeah? converting this is you go through a process of, and this is a good one actually, guys. Thanks, Miss Piri. This is a good one because what you have to do is you say 7 F F F F. It's a lot, huh? Whoa. So 7 F F F. How many Fs? 4 Fs, right? 4 Fs. 7. Wow, this is a long one. 1 4. So and this is a good one. If you know you refuse Miss Piri, I think let's do this together, right? This will be fun. I guess a nice way of wasting time remaining. So if you remember, the first step we said is you, and I don't know if this is where the no question came in this period, but the first step is you first of all get the equivalent hexadecimal symbols for these things you have here. 7 is 7, F is, what is F? 15? 15, 15, 15. If this is what we meant by ignoring, then yes. 1, 4. What's the next step? Get the powers of 16. 16 power 0, 16 power 1, 16 power 2, 16 power 3, 16 power 4, 16 power 5. Well, we should have brought this in the quiz or something. 16 power 6. Why did you ask me to 16 power 7, right? Should have brought it, now it's gone, I guess. Anyway, we'll find another. There are plenty of questions we can recycle. It's not a problem. So you evaluate the powers of 16, right? 16 power 0 is 1. 16 to power 1 is 16, right? Same drill here. 16 power 2. Oops. 16 to power 3. 16 to power 4. 16 to power 5, and Mr. Mwalimu has taught you about this, right? You just expand this, right? These are large numbers. This is why it was masked out or something. 16 power 6. This is going to be masked out. This is a huge number working with. 16 power 7 here. Why did you ask me, Spirit? Could have brought this in the test. Now, so here's the thing, right? The quiz. So here's the thing, right? And then the next step is we multiply these magnitudes by the equivalent decimal number. So we come here. It's 7 times this. We come here, it will be 15 times this number. We come here, it will be 15 times this number here. From here, it will be 15 times this number. Come here, it's like Sisyphus. Now we're doing the same thing over and over again, times this number, right? We come here, it will be 7 times 256. Then 1 times 16 is obviously going to be 16 or something, right? If I were you, as you are practicing, please, I implore you, do this stepwise until the method sinks in, right? That way you avoid mistakes, right? And then the final step is sum of products, right? So all you do is we use Mr. Mwalimu's summation thing he gave us. And so our answer is, wow, 2,147,481,364. That's nice. So we can confirm this by just coming here, hex 7 1 2 3 4 7 1 4. What is the equivalent hex? Oh, there we go, right? On point. Is this making sense? We should have brought this. Why did we do this? This memory. Are there any other questions that people might have?
So Dr. Lydon, talking about the quiz and how we should answer these questions, like for me, I will just follow the same setup you are using in terms of converting from hex to decimal. Do we have to write on a separate answer sheet and then scan the document, or like you said before?
No. Well, so for the test, you will be told, right? Usually, right? This question, and I'm laughing because I know where this question is coming from. So usually in the assessments, it's when it's explicitly said to say show your working, you must show the working because there are marks allocated to the working, and it's for your own good because sometimes there are small little marks that are allocated by you just showing part of the working, even though the final answer is wrong. But if you show your working, you get some marks. So to answer your question, unless it's explicitly stated, you can just ignore and not just show your working. Like for the quiz, this is the thing with the quiz, right? Because it's going to be online. We know that some of you are just going to go to some online website and just say, and I know you, right? Everybody, we know what you are. You just hear and you say hex to decimal calculator, right? Calculator, right? And you are patiently waiting for the quiz, right? And you find this link, you even bookmark it on your phone. Lighton has a question. Lighton tells you to say, can you convert 7 FFFF414 to decimal? And I know you copy this, and then you come here, you say, boom, and then you convert, and then you type in that answer. And if it says so, then fine, you get a free mark or something. That's fine. I mean, it's an unpaid book. These are open book assessments anyway. But unless if it says explicitly that you show working, Patrick, then you don't have to, unless if you want to waste time. I'm sharing that link in case you want to go through. There are plenty of calculators out there. Some of you probably use spreadsheets for this. It's fine, right? But if I were you, I'd just learn the process itself, because it turns out that if you learn the process, learning how to do some other computations that are going to do, like things like sign magnitude and ones complement and tens complement, becomes a lot easier, right? You want to learn how to do these things. Are there any other questions? All right. So between now and yes, hi.
Oh yes. Using the last formula that we used.
Which formula is that?
The drawing
This.
that you made, the 16 here, then
This
not
drawing.
that one.
Which one?
Yeah, that one. So let's try to use 123. Then when we find the answer, the last answer, then we try to prove it using the same answer, using the other formula that we are from using the formula that we're converting the F's, the 15, 15.
I see what you mean, memory. So what you're saying is we should, this is 123, is this base 16 or base 10?
Base 2.
No, this can be base 2. What do you mean? Is this, the 123, is this base 16 or base 10?
Oh, no, it's base 10, sorry, sir.
Okay, so 123 base 10, you want us to derive base 16 and then we go back in the opposite direction, right?
Yes.
It's easy, right? So when we're converting from decimal to hexadecimal, it's repeated division. So we use this table we're talking about, right? Where we repeatedly divide 123 by 16. It shouldn't be really that hard. If I were you, I would draw these things actually with your pen, right? So we're going to have a 123 somewhere here. Wow. 123 here. Sorry, I'm using my mouse here, so it's going to be a bit of a challenge. 1, 2, 3. My 1, 2, 3. I think your young brothers and sisters will probably laugh that this is how he writes or something. Anyway, I hope that looks like a 2. So we're saying the first thing we have to do is we divide 123 by 16, right? So you obviously go to your calculator. You're allowed to use calculators, scientific calculators actually. So if I were you, if you don't have a calculator, buy a calculator and then practice how to use it so that you know the shortcuts and whatnot. So 16 to 123 is 7, right? Remainder, this times 16. The remainder is 11. 1, 1. We do the same thing. We say 16 into 7. It can't, right? Or it's 0 remainder, 7. The other final step is for all numbers that are equal to 10 and above, you use those hex symbols, A through F. We know 10 is A, B is 11, so this is B. And then this is going to be 7. So the answer here is 7B, base 16, right? And we can prove this. We go here, we'll say, what is 123 base 10? It's 7B. Now, your other question is, how then do we go back in the opposite direction? Well, converting from hex to decimal, we just repeatedly multiply, right? We go through a process where we say 7B. We use the same process here where we say 7B. The first step is we get the equivalent decimal symbol. 7 is 7. B is 11. What else do we do as step number 2? we get the powers of 16, beginning 16 power 0. This is going to be 16 to power 0. This is going to be 16 to power 1. Wow, 16 power 1. Sorry about that. My writing is horrible. 16 power 1. And then we evaluate the powers of 16. This, any number to power 0, they told us is 1. 16 to power 1 is 16. And then we multiply the derived X symbols with the evaluated powers of 16. 11 times 1 is 11. 16 times 7, I'm ashamed to say I don't know. I'll have to calculate. 16 times 7 is, 16 times 7 is 112. And then what do we do with this? We get the sum of products. So we add 112 plus 11. 112 plus 11 is just going to be 123. You understand this? Is this making sense now? This is going to be 123. I want us to check here. What is 112? 112 plus 11, right? So you get back your 123. Is this making sense? Are you still there?
Yes, sir.
Yes, sir, we're here.
Yeah,
Yeah.
yeah,
Okay.
it's making sense.
All right. So what I encourage you to do, right? It's a marathon we are working with here. For this to work, do not leave this until the end. So between now and 16 hours tomorrow, just do a bit of practice. There are some problems that I've included, and you will understand to a question. I will upload the lab for the other thing. I do apologize, and I respond to that, and I'll upload the lab. I'll also upload some practice questions, more practice questions for these conversions. But between now and tomorrow, just make sure that you get the decimal to hexadecimal conversion and the hexadecimal to decimal conversion by working through some of these problems that I highlighted here, these mark addresses. So beginning slide number 59, 60, 61, just see if you can work through these problems, right? That'll be good, right? And then tomorrow we can start binary representation. And then very soon I want us to wrap up number system so that we can start doing the good stuff. Okay. I'll see you when you see me, which is tomorrow, 16 hours promptly. Thank you very much. And I'll share this as soon as the rendering is done. Thanks. Bye-bye.
All right, bye, sir. Bye-bye. Can someone kindly stop the recording?